Distributed transactions and consensus. Consensus is one of the most important and fundamental problems in distributed computing. On the surface, it seems simple. Informally, the goal is simply to get several nodes to agree on something. You might think that this shouldn't be too hard. Unfortunately, many broken systems have been built in the mistaken belief that this problem is easy to solve. Although consensus is very important, the section about it appears late in this book because the topic is quite subtle, and appreciating the subtleties requires some prerequisite knowledge. Even in the academic research community, the understanding of consensus only gradually crystallized over the course of decades, with many misunderstandings along the way. Now that we have discussed replication Chapter 5, transactions Chapter 7, system models Chapter 8, linearizability, and total order broadcast this chapter, we are finally ready to tackle the consensus problem. There are a number of situations in which it is important for nodes to agree. For example, leader election in a database with single leader replication. All nodes need to agree on which node is the leader. The leadership position might become contested if some nodes can't communicate with others due to a network fault. In this case, consensus is important to avoid a bad failover, resulting in a split-brain situation in which two nodes both believe themselves to be the leader. See handling node outages on page 156. If there were two leaders, they would both accept rights and their data would diverge, leading to inconsistency and data loss. Roman 12. Atomic commit is formalized slightly differently from consensus. An atomic transaction can commit only if all participants vote to commit, and must abort if any participant needs to abort. Consensus is allowed to decide on any value that is proposed by one of the participants. However, atomic commit and consensus are reducible to each other. Non-blocking atomic commit is harder than consensus. See three-phase commit on page 359. Atomic commit in a database that supports transactions spanning several nodes or partitions. We have the problem that a transaction may fail on some nodes, but succeed on others. If we want to maintain transaction atomicity in the sense of ACID, see atomicity on page 223, we have to get all nodes to agree on the outcome of the transaction. Either they all abort/roll back if anything goes wrong, or they all commit if nothing goes wrong. This instance of consensus is known as the atomic commit problem. Roman 12. The impossibility of consensus. You may have heard about the FLP result named after the authors Fisher, Lynch, and Patterson, which proves that there is no algorithm that is always able to reach consensus if there is a risk that a node may crash. In a distributed system, we must assume that nodes may crash, so reliable consensus is impossible. Yet, here we are, discussing algorithms for achieving consensus. What is going on here? The answer is that the FLP result is proved in the asynchronous system model. See system model and reality on page 306, a very restrictive model that assumes a deterministic algorithm that cannot use any clocks or timeouts. If the algorithm is allowed to use timeouts, or some other way of identifying suspected crashed nodes, even if the suspicion is sometimes wrong, then consensus becomes solvable. Even just allowing the algorithm to use random numbers is sufficient to get around the impossibility result. Thus, although the FLP result about the impossibility of consensus is of great theoretical importance, distributed systems can usually achieve consensus in practice. In this section, we will first examine the atomic commit problem in more detail. In particular, we will discuss the two-phase commit 2PC algorithm, which is the most common way of solving atomic commit and which is implemented in various databases, messaging systems, and application servers. It turns out that 2PC is a kind of consensus algorithm, but not a very good one. By learning from 2PC, we will then work our way toward better consensus algorithms, such as those used in Zookeeper Zab and Raft. Atomic commit and two-phase commit 2PC. In Chapter 7, we learned that the purpose of transaction atomicity is to provide simple semantics in the case where something goes wrong in the middle of making several writes. The outcome of a transaction is either a successful commit, in which case all of the transaction's writes are made durable, or an abort, in which case all of the transaction's writes are rolled back, i.e. undone or discarded. Atomicity prevents failed transactions from littering the database with half-finished results and half-updated state. This is especially important for multi-object transactions. See single object and multi-object operations on page 228, and databases that maintain secondary indexes. Each secondary index is a separate data structure from the primary data. Thus, if you modify some data, the corresponding change needs to also be made in the secondary index. Atomicity ensures that the secondary index stays consistent with the primary data. If the index became inconsistent with the primary data, it would not be very useful. From single node to distributed atomic commit for transactions that execute at a single database node, atomicity is commonly implemented by the storage engine. When a client asks the database node to commit the transaction, the database makes the transaction's writes durable, typically in a write-ahead log. See making B-trees reliable on page 82, and then appends a commit record to the log on disk. If the database crashes in the middle of this process, the transaction is recovered from the log when the node restarts. If the commit record was successfully written to disk before the crash, the transaction is considered committed. If not, any writes from that transaction are rolled back. Thus, on a single node, transaction commitment crucially depends on the order in which data is durably written to disk. First the data, then the commit record. The key deciding moment for whether the transaction commits or aborts is the moment at which the disk finishes writing the commit record. Before that moment, it is still possible to abort due to a crash, but after that moment, the transaction is committed even if the database crashes. Thus, it is a single device, the controller of one particular disk drive, attached to one particular node, that makes the commit atomic. However, what if multiple nodes are involved in a transaction? For example, perhaps you have a multi-object transaction in a partition database, or a term partition secondary index in which the index entry may be on a different node from the primary data. See partitioning and secondary indexes on page 206. Most NoSQL distributed data stores do not support such distributed transactions, but various clustered relational systems do. See distributed transactions in practice on page 360. In these cases, it is not sufficient to simply send a commit request to all of the nodes and independently commit the transaction on each one. In doing so, it could easily happen that the commit succeeds on some nodes and fails on other nodes, which would violate the atomicity guarantee. Figure 9-9. A successful execution of two-phase commit to PC. Figure 9-10. The coordinator crashes after participants vote yes. Database 1 does not know whether to commit or abort. Some nodes may detect a constraint violation or conflict, making an abort necessary, while other nodes are successfully able to commit. Some of the commit requests might be lost in the network, eventually aborting due to a timeout, while other commit requests get through. Some nodes may crash before the commit record is fully written and roll back on recovery, while others successfully commit. If some nodes commit the transaction, but others abort it, the nodes become inconsistent with each other, like in Figure 7-3. And once a transaction has been committed on one node, it cannot be retracted again if it later turns out that it was aborted on another node. For this reason, a node must only commit once it is certain that all other nodes in the transaction are also going to commit. A transaction commit must be irrevocable. You are not allowed to change your mind and retroactively abort a transaction after it has been committed. The reason for this rule is that once data has been committed, it becomes visible to other transactions, and thus other clients may start relying on the data. This principle forms the basis of read-committed isolation, discussed in Read Committed on page 234. If a transaction was allowed to abort after committing, any transactions that read the committed data would be based on data that was retroactively declared not to have existed, so they would have to be reverted as well. It is possible for the effects of a committed transaction to later be undone by another, compensating transaction. However, from the database's point of view, this is a separate transaction, and thus any cross-transaction correctness requirements are the application's problem. Two-phase commit is an algorithm for achieving atomic transaction commit across multiple nodes, i.e. to ensure that either all nodes commit or all nodes abort. It is a classic algorithm in distributed databases. 2PC is used internally in some databases and also made available to applications in the form of XA transactions, which are supported by the Java Transaction API, for example, or via WS Atomic Transaction for SOAP web services. The basic flow of 2PC is illustrated in Figure 9-9. Instead of a single commit request, as with a single node transaction, the commit/abort process in 2PC is split into two phases, hence the name. Don't confuse 2PC and 2PL. Two-phase commit 2PC and two-phase locking. See two-phase locking 2PL on page 257 are two very different things. 2PC provides atomic commit in a distributed database, whereas 2PL provides serializable isolation. To avoid confusion, It's best to think of them as entirely separate concepts and to ignore the unfortunate similarity in the names. 2PC uses a new component that does not normally appear in single-node transactions, a coordinator also known as transaction manager. The coordinator is often implemented as a library within the same application process that is requesting the transaction, for example embedded in a Java EE container, but it can also be a separate process or service. Examples of such coordinators include Narayana, Jatam, BTM, or MSDTC. A 2PC transaction begins with the application reading and writing data on multiple database nodes. As normal, we call these database nodes participants in the transaction. When the application is ready to commit, the coordinator begins phase 1. It sends a prepare request to each of the nodes, asking them whether they are able to commit. The coordinator then tracks the responses from the participants. If all participants reply yes, indicating they are ready to commit, then the coordinator sends out a commit request in phase 2, and the commit actually takes place. If any of the participants replies no, the coordinator sends an abort request to all nodes in phase 2. This process is somewhat like the traditional marriage ceremony in Western cultures. The minister asks the bride and groom individually whether each wants to marry the other, and typically receives the answer I do from both. After receiving both acknowledgements, the minister pronounces the couple husband and wife. The transaction is committed, and the happy fact is broadcast to all attendees. If either bride or groom does not say yes, the ceremony is aborted. From this short description, it might not be clear why two-phase commit ensures atomicity, while one-phase commit across several nodes does not. Surely the prepare and commit requests can just as easily be lost in the two-phase case. What makes 2PC different? To understand why it works, we have to break down the process in a bit more detail. When the application wants to begin a distributed transaction, it requests a transaction ID from the coordinator. This transaction ID is globally unique. The application begins a single-node transaction on each of the participants and attaches the globally unique transaction ID to the single-node transaction. All reads and writes are done in one of these single-node transactions. If anything goes wrong at the stage, for example, a node crashes or a request times out, the coordinator or any of the participants can abort. When the application is ready to commit, the coordinator sends a prepare request to all participants, tagged with the global transaction ID. If any of these requests fails or times out, the coordinator sends an abort request for that transaction ID to all participants. When a participant receives the prepare request, it makes sure that it can definitely commit the transaction under all circumstances. This includes writing all transaction data to disk. A crash, a power failure, or running out of disk space is not an acceptable excuse for refusing to commit later, and checking for any conflicts or constraint violations. By replying yes to the coordinator, the node promises to commit the transaction without error if requested. In other words, the participant surrenders the right to abort the transaction, but without actually committing it. When the coordinator has received responses to all prepare requests, it makes a definitive decision on whether to commit or abort the transaction, committing only if all participants voted yes. The coordinator must write that decision to its transaction log on disk so that it knows which way it decided in case it subsequently crashes. This is called the commit point. Once the coordinator's decision has been written to disk, the commit or abort request is sent to all participants. If this request fails or times out, the coordinator must retry forever until it succeeds. There is no more going back. If the decision was to commit, the decision must be enforced, no matter how many retries it takes. If a participant has crashed in the meantime, the transaction will be committed when it recovers since the participant voted yes. It cannot refuse to commit when it recovers. Thus, the protocol contains two crucial points of no return. When a participant votes yes, it promises that it will definitely be able to commit later, although the coordinator may still choose to abort. And once the coordinator decides, that decision is irrevocable. Those promises ensure the atomicity of 2PC. Single-node atomic commit lumps these two events into one, writing the commit record to the transaction log. Returning to the marriage analogy, before saying I do, you and your bride/groom have the freedom to abort the transaction by saying no way, or something to that effect. However, after saying I do, you cannot retract that statement. If you faint after saying I do and you don't hear the minister speak the words you are now husband and wife, that doesn't change the fact that the transaction was committed. When you recover consciousness later, you can find out whether you are married or not by querying the minister for the status of your global transaction ID, or you can wait for the minister's next retry of a commit request since the retries will have continued throughout your period of unconsciousness. We have discussed what happens if one of the participants or the network fails during 2PC. If any of the prepare requests fail or timeout, the coordinator aborts the transaction. If any of the commit or abort requests fail, the coordinator retries them indefinitely. However, it is less clear what happens if the coordinator crashes. If the coordinator fails before sending the prepare requests, a participant can safely abort the transaction, but once the participant has received a prepare request and voted yes, it can no longer abort unilaterally. It must wait to hear back from the coordinator whether the transaction was committed or aborted. If the coordinator crashes or the network fails at this point, the participant can do nothing but wait. A participant's transaction in this state is called in doubt or uncertain. The situation is illustrated in Figure 9-10. In this particular example, the coordinator actually decided to commit, and database 2 received the commit request. However, the coordinator crashed before it could send the commit request to database 1, and so database 1 does not know whether to commit or abort. Even a timeout does not help here. If database 1 unilaterally aborts after a timeout, it will end up inconsistent with database 2, which has committed. Similarly, it is not safe to unilaterally commit, because another participant may have aborted. Without hearing from the coordinator, the participant has no way of knowing whether to commit or abort. In principle, the participants could communicate among themselves to find out how each participant voted and come to some agreement, but that is not part of the 2PC protocol. The only way 2PC can complete is by waiting for the coordinator to recover. This is why the coordinator must write its commit or abort decision to a transaction log on disk before sending commit or abort requests to participants. When the coordinator recovers, it determines the status of all in-doubt transactions by reading its transaction log. Transactions that don't have a commit record in the coordinator's log are aborted. Thus, the commit point of 2PC comes down to a regular single-node atomic commit on the coordinator. Two-phase commit is called a blocking atomic commit protocol due to the fact that 2PC can become stuck waiting for the coordinator to recover. In theory, it is possible to make an atomic commit protocol non-blocking so that it does not get stuck if a node fails. However, making this work in practice is not so straightforward. As an alternative to 2PC, an algorithm called three-phase commit 3PC has been proposed. However, 3PC assumes a network with bounded delay and nodes with bounded response times. In most practical systems with unbounded network delay and process pauses, see Chapter 8, it cannot guarantee atomicity. In general, non-blocking atomic commit requires a perfect failure detector, i.e. a reliable mechanism for telling whether a node has crashed or not. In a network with unbounded delay, a timeout is not a reliable failure detector, because a request may time out due to a network problem even if no node has crashed. For this reason, 2PC continues to be used, despite the known problem with coordinator failure.